So chapter 11 is on liquids. If you are paying attention, chapter 12 is on solids, okay? These two are put together because liquids and solids have a lot of characteristics in common. Okay, liquids, solids, what's missing? Gases. We've already covered gases, okay? I believe chapter 10 is the gases and the gas laws. We've already covered that, okay? And liquids and solids behave very differently from gases. One of the things that makes them very different, liquids and solids are very incompressible. You can't change the volume of a liquid or a solid hardly at all, if at all. Whereas gases can be compressed quite a bit. Okay? And if you think about it, let's think about this in terms of density. What's the formula for density? What divided by what? Mass over volume. Well, for a gas, if you can change the volume, gases can have varying densities. If you change the temperature, the density of a gas changes. Whereas liquids and solids, because their volumes don't change, they have constant density. Okay? Liquids and solids have many things in common because of the way that they're held together. Okay? Liquids and solids, their particles are held relatively close together as opposed to gases. Their particles are farther apart. And this, what's holding liquids and solids together, is the big topic in this chapter. Okay? This term, intermolecular forces. You did this in Chem 1, right? And let's just see if you recall this. Hopefully your teachers went over this. What does the prefix inter mean? Like you see that prefix, like if any of you are Major League Baseball fans, when you see the Nationals, who are in the National League, play a team from the American League, they say that that is an interleague game. What does the prefix inter mean? Yeah. Between. Okay? They call it an interleague game because it's between two different leagues. Between molecules. Okay? So we're talking about, I have one entire water molecule, I have a separate water molecule. What are the forces that exist between them? Okay. What's the other prefix that we will sometimes talk about? Do you know what the prefix is for within? Yeah, do you know? Intra. So when the Nationals play the Phillies, two teams that are in the same league, that's an intra-league game, within. Okay? And let's think about what are the two types of intra-molecular forces that hold compounds together. What are the two types of compounds out there? Ionic and covalent. So there's only two types of intra forces. It's either an ionic bond or a covalent bond that holds a compound together. We're going to focus on inter. And there are three types. London dispersion forces. That's your first type. You have my permission to abbreviate this LDFs. Okay? Your second type, they're called dipole-dipole forces, or dipole-dipole attraction. And hydrogen bonding is the third type. And I've presented them in order of their strength. London dispersion forces are very weak forces. Dipole-dipole attraction is a little bit stronger. Hydrogen bonding is the strongest of those three. Okay, so let's look at each one individually. And those three types, those should be familiar to you from Chem 1, but I don't know how much depth your teachers in Chem 1 will go into. We're going to go into some depth here, okay? First and foremost, ladies and gentlemen, I want you to know that every single one, all covalent compounds contain London dispersion forces, okay? Now, London dispersion forces, guys, also exist within a sample of a noble gas. Okay, they hold noble gas atoms together. I should have phrased this a little bit differently. What I am trying to say here with this nonpolar business here is that if a covalent compound is nonpolar, then London dispersion forces are its only intermolecular force. Okay? But all covalent compounds have London dispersion forces. If something is nonpolar, then that's all that it will have. Okay? And I want you guys to understand why these forces exist. And I don't think your Chem 1 teachers really go into this. Okay, but let's use an example we've used multiple times in here. Let's use methane. Okay. Remind me, anytime you draw just a single line like that in a Lewis structure, what does that represent? A shared pair of electrons, okay? Well, these two electrons that are between this carbon and this hydrogen, they stay in this sort of general area, but I want you guys to make sure you understand, electrons are not static, okay? They don't sit still. They move, okay? They have rotational movement, they have vibrational movement, they move. All right, now they're not flying all over the place. They have to stay in this general area, but they move. Here's the thing. Even though this is nonpolar, these electrons are moving really, really, really fast. They're shaking in place like this. If you were able to pause the molecule and freeze the electrons in their places, chances are these electrons are not going to be in these perfect tetrahedral positions. They move. They're going to be sometimes a little bit more congregated on one side of the molecule than the other. Now, is that going to last long? No. The word instantaneous means for an instant. For just an instant, this non-polar molecule, just for an instant, could be slightly polar, just slightly, because these electrons have motion to them. Okay? Instantaneous dipole. It's polar, but barely polar, and only for a split second. Okay? Which, if this guy is just a teensy bit polar for a split second, that might cause the methane molecule just next to it to be slightly polar for a split second as well. It can induce a dipole in the molecule next to it. Okay? Now, these forces, guys, are relatively weak because, number one, they don't last very long. They're instantaneous. Number two, when we say that this molecule is an instantaneous dipole, it's barely polar. Just barely. Anyway, so that causes these forces to be very short-lived, very weak. There is a vocabulary word here that is super duper important. Highlight it, circle it, draw flashing lights all around it. I don't know how you draw flashing lights, but figure it out. All right? That's an important vocabulary word. Polarizability, which is, it says, is the ease with which the electron cloud of an atom can be induced into that momentary dipole. Okay, polarizability. And here's the gist, ladies and gentlemen. The more electrons a molecule contains, we say the more polarizable it is. I'm going to draw a second molecule up here on the board for comparison. I mean, I want you just at first glance, just looking at these molecules. Which one looks like it has more electrons to it? Yeah, I mean, there's dots all over the place here. Remember, each dot represents an electron. Okay? What this is saying is, because this is, and you can say it multiple ways. You can say because this is a larger molecule. I mean, bromine is definitely larger in size than hydrogen. Because it's larger, because it contains more electrons, okay? Because it has a greater molar mass. These are all ways to say the same thing. This is the more polarizable molecule. Now, what does that mean? It's more easily made to be polar for that split second. The more electrons there are, the easier it is for this guy to be momentarily polar. Both of these molecules are nonpolar molecules. That means they both have London dispersion forces only, but here's the catch. This one's London dispersion forces are just a little bit stronger. The more polarizable a molecule is, the stronger its LDFs will be. So this one has, they both have LDFs only, but this one's London dispersion forces are just a little bit stronger. Now guys, are you going to be asked directly which one is more polarizable? No, you're not. Here's what you will be asked. You will be asked, more likely, which one has the higher melting point, or which one has the higher boiling point. It doesn't actually matter which one they ask you, because the answer is going to be the same. Tell me this, because this is something that drives me crazy. All right? If you are melting or boiling something, you're breaking bonds, right? Nod your heads. Okay? I want to make sure you understand what kind of bonds you're breaking. And here's how you're going to prove to me that you know this answer. If you put a pot of water on the stove, you've add heat to it, it starts to boil, you see a vapor coming out of the pot. What's in that vapor? H2O. You had H2O in the pot in liquid form, you have H2O in the gaseous form. So it's H2O before, it's H2O after. What did you break to boil it? Intermolecular forces. Too many times I think people think that melting and boiling, you're breaking intra, and that's not true. Because guys, think about it. Think how crazy that would be. If you boiled a pot of water on the stove, and boiling meant breaking intramolecular bonds, what would be in the gas? Hydrogen and oxygen, two flammable gases. That would not be good. Okay? So when you melt or boil something, you are breaking intermolecular forces. Well, didn't we just say, even though both of these have LDFs only, this one's LDFs are just a little bit stronger? Think about it. If this one is held a little bit more tightly together, its molecules, don't you think it's going to take a higher temperature to finally break those bonds? Doesn't that make sense? So this guy would have a higher melting point, a higher boiling point. It doesn't matter which one they ask. The stronger the intermolecular force, the higher the melting and boiling point will be. Okay. Just want you to be aware of this term. I don't imagine you're ever going to see it. This is kind of an out-of-date term. If you ever see this, van der Waals forces, it just means the same thing. They're London dispersion forces. We don't use this term anymore. I don't think your textbook uses it. Just to make sure if you ever do see it, you know what that means. Okay. Let's talk about the second type of intermolecular force, dipole-dipole forces. Dipole, ladies and gentlemen, that's just a fancy word that means what? Polar. Okay? So these are forces that exist when you're dealing with polar molecules. These guys don't have dipole-dipole forces. Things that are polar, they do. Okay? And I'm going to use some incredibly fancy art here. That's a molecule, ladies and gentlemen. That blob is a molecule. Okay? What does it mean? Can somebody put this in your own words? What does it mean for an entire molecule to be polar? What does that really mean? Yeah. One end or one side of the molecule is a little bit more positive, and the other end is a little more negative. That's a polar molecule. That just means that in the molecule next to it, we're going to get a force of attraction right there. Okay? That is a dipole-dipole attraction right there. Okay? Between the positive end of one molecule, polar molecule, and the negative end of another. So we're going in a progression here. All covalent compounds have London dispersion forces. All of them. If it's a nonpolar molecule, then that's all it has. If it's polar, it has LDFs and it has dipole-dipole forces. If it's polar, it might have this third kind. Hydrogen bonding. Not everything that's polar has hydrogen bonding. Some things do and some things don't. Okay? First of all, obviously, to qualify to have hydrogen bonding, it's got to have hydrogen in it. But it's not hydrogen in just anything. It's got to have one of these three elements in the compound as well. NOF, NOF. What's so special about these guys? They are very electronegative elements. That's a term that's on your test next week. What does that mean? An element that is very electronegative is an element that does what? Attracts what? A shared pair of electrons towards itself. Okay? Okay, so let me just recap here a little bit. All covalent compounds have LDFs. If they're nonpolar, then that's all they have. If it's a polar molecule, it has LDFs, it has dipole-dipole. It might also have hydrogen bonding. And guys, hydrogen bonding is just a very specific type of dipole-dipole attraction. It's a strong type. And that's what's being illustrated in these pictures. It's the force that exists between the hydrogen of one molecule and, for example, the oxygen in another. Okay. So I'll draw it up here. This is good review for our test. Okay. Is water covalent, yes or no? Okay. So does it have London dispersion? Yep. Is it a polar molecule? Yes. So what else does it have? It has dipole-dipole. Does it have hydrogen bonding? Yes, it does. It has all three, which means water is a compound that's held pretty tightly together. One water molecule and its neighbor are held pretty tightly together. Okay. I have this model. This is basically ice. Okay, this is what ice looks like. And what you've got here, and actually you guys tell me, what's the shape of water? Bent. Okay, in this model, the white pieces, focus on these white connectors, there is that bent shape. Okay, each of the white pieces is showing you the the bent shape. The green connectors, if you'll notice, are connecting one water molecule to another. The green pieces are representing the intermolecular forces. I'll pass it. Everybody likes hands-on. Okay. There is one final thing I want to say about hydrogen bonding. Okay, you have to be careful with hydrogen bonding, guys, because a lot of people will see hydrogen in a compound and they just automatically, oh, it's got hydrogen bonding. Not necessarily. I'm telling you that one of these compounds has hydrogen bonding and the other one doesn't. Okay, well, let's just think this out a little bit here. These are both covalent, right? Say yes. Yes, okay. So they both have London dispersion forces. This is good review. What's the shape of this molecule right here? I've even drawn it to sort of illustrate that shape. Trigonal planar, okay. Good review. What's the bond angle here? 120. What's the hybridization? sp2. Okay. Focus just on the carbon here. What's the shape, the molecular geometry around that carbon? Tetrahedral. What's the angle? 9.5. Hybridization? sp3. Okay. Is this molecule polar or nonpolar? You tell me. Okay, well, what was the shape again? Tell me one more time. Trigonal planar. Isn't trigonal planar a shape that usually cancels out the polarity of the bonds? But what's the problem? Okay, the terminal atoms are not all the same element. So is this guy polar or nonpolar? He's polar. So he has dipole-dipole. I'm going to abbreviate. Don't write this on a test. He's got dip-dip. Dip-dip. Okay. This molecule, also polar. Also has dipole-dipole. But one has hydrogen bonding and the other doesn't. Let's read the statement. It says, hydrogen bonding only occurs if hydrogen is chemically bonded covalently, intramolecularly bonded to NO or F. Tell me, which one has hydrogen bonding, the left or the right? You got it. This one doesn't. Okay? So, be very careful when you are asked to say what intermolecular forces a compound has. Be careful if you see hydrogen. Don't just be impulsive and say, ooh, it's got hydrogen bonding. Just be careful. Make sure that it actually does. Okay? So here's the ultimate question. This is our last slide. I'm just tying this all together. I'm presenting you with 3 molecules here. We've looked at all 3 already. Which one has the highest melting or boiling point? Doesn't matter which one I'm asking you. Do they all have LDFs? Yes or no?
Yes.
Yes, they do. Okay. Do they all have dipole-dipole forces? Which one doesn't? Okay, so this guy's nonpolar. That's all he has. We said this was polar, so it's got dipole. Does this one have hydrogen bonding? No. But this one has all 3. All 3 types of forces. Okay? So guys, can you see that this compound, this molecule, is the one that has the strongest intermolecular forces? A sample of this compound will be held the most tightly together of all 3. This one will have the highest melting or boiling point because it has the most intermolecular forces. The biggest molecule? Technically, yes, it is, but you only think about which molecule is larger in size. Only think about that if you're comparing 2 things that only have LDFs. So this is bigger, but the bigger issue at play here is the fact that this has 3 intermolecular forces, where this only has 2, this only has 1. Okay? So, the take-home message here, guys, is that what we're about to take a test on next week, like shapes, polarity, all of this, drawing Lewis structures, you can't just take the test next week and say, okay, I'm done with it. You need that material in order to answer these questions in our next unit. Okay? I will stop there. Okay?